today. I'd like to welcome you all to the fourth in our spring series of webinars on using Statgraphics Centurion. I've been real encouraged by the large number of people who've been logging on to watch, and as long as you keep logging on to watch, I'll keep going and covering more and more topics. Today's topic is regression analysis. Now, this is one of the topics that was suggested by one of the viewers in the first couple seminars, and I do invite you all to suggest topics to me that you'd like to see covered. My name is Neil Polhemus, by the way. I am in charge of developing Statgraphics and have been for quite a few years. As I said, the topic today is regression analysis, and in terms of what people search for on our website, the two largest search terms, most frequent search terms, are regression analysis and also analysis of variance. And we'll have to do a webinar on analysis of variance here in the near future. The outline for today's talk is the following. I'm going to spend just a few minutes talking about regression models, what the general format of a regression model is, and then I'm going to go through a number of different examples. I've picked out several examples having to do with regression models involving a single X, that's a single predictor variable, and several examples involving multiple X's. As far as a single X is concerned, we'll talk about simple regression, which is an important procedure in Statgraphics for fitting linear and transformable nonlinear models involving one Y and one X. We'll talk about the nonlinear regression procedure, where you can actually type in any function, be it linear or nonlinear, and have the procedure do a nonlinear least squares search for the optimal parameters. We'll talk about the calibration problem. The calibration problem has to do with predicting X given Y rather than the typical Y given X scenario. And then we'll also talk about the comparison of regression lines. That's the case where I fit several regression lines, one to each group of data, and do statistical tests to determine whether or not there's a significant difference between the regression lines as fit to the different groups. Very interesting procedure, important procedure. The examples on multiple regression, I've picked out three. First off, we're going to do a standard multiple regression where the response variable is a typical continuous measurement, like a strength or a diameter or something like that. We'll talk about what Statgraphics does in terms of helping you pick a good model, a good regression model, and I'll actually look at two options, a stepwise option and an option to do all possible regressions. Then I'll also look at two special cases, a logistic regression, where rather than being a continuous variable, the response is a proportion or a probability. You know, what's the probability of having a defective item, for example, as a function of various input variables. And finally, we'll talk about Poisson regression. In a Poisson regression, the response variable is a count. Now, when I was putting together this webinar, I noticed that there were quite a number of procedures in Statgraphics to do regression analysis. What they have in common, though, is they all involve, first off, a dependent variable, a dependent or response variable, which we're going to call Y. This is the variable that we're going to try to predict based upon our regression model. They also all involve independent variables, one or more independent variables, X, X1 up to XK as I've written it here. And finally, they also involve an error term in epsilon. Since we are talking about statistics, and we're talking about fitting models to real data, there's always some random component. And basically the regression models that we'll be fitting will express the response variable, the dependent variable y, as some function of those x's, be it linear, nonlinear, whatever, plus noise, plus error. So it's y is a function of x plus epsilon. Now, where the different procedures in Statgraphics vary is in the characteristics of the y's and the x's. And in the handout for the slide that you can download, incidentally, after the webinar is over, I've listed 16 different procedures in Statgraphics that have to do with fitting regression models. On the first page here, you see a list of 5 of those. For all of the procedures on this page, simple regression, polynomial regression, and so forth, the dependent variable is continuous. For the first 4, there is a single continuous independent variable, so you've got basically one y and one x, with the exception of the comparison of regression lines, where you have both a continuous x and some categorical variable that differentiates different observations. There are also a lot of procedures in Statgraphics, and here's a second page of my list, that have to do, again, with modeling a continuous response variable. Something like a dimension or a temperature or something like that, but involve 2 or more continuous independent variables. And when you've got 2 or more, then we're talking about things like multiple regression and ridge regression, partial least squares, and so forth. There's also a very special procedure, and we're going to have to do a whole webinar on this one, the general linear models procedure. This is a procedure that can take 1 or more y variables and 2 or more continuous or categorical x variables. You can do a lot of what the other procedures do as special cases in the general linear models procedure, but you can do other interesting types of analyses like repeated measures, designs, and split plots and things like that. That's beyond what I'm going to be talking about today, but again, if the interest holds, we'll talk about some of those special topics at a later date. We also have in Statgraphics, as I had mentioned earlier, some special procedures for cases where the dependent variable is not continuous. For example, if the dependent variable is proportions, then we might want to do a logistic regression or probit analysis or something like that. If the dependent variable, the y variable, is counts, then we've got either a Poisson regression or a negative binomial regression. And finally, there's also a procedure, a special procedure for fitting life data. That is where the response variable is time to failure. And there's some special considerations there. That's also outside the scope of what we're going to talk about today. But again, we'll probably have a webinar or 2 on handling life data. Okay. Now, as I said, you can download and print out this table and take a look at it, and hopefully that will help you pick out the proper regression procedure. Now, what I'd like to do, though, is I'd like to get right into using Statgraphics to fit regression models. And the first example I'm going to start with today is a stability study. Now, a stability study is a study where you take samples of some product that you're producing at different ages. For example, we have a data file that we're going to be looking at here where there are samples of a product. We've taken samples anywhere from 8 weeks after it was produced down, I think it's to about 42 weeks. The critical quantity in this particular product is the percent of available chlorine. And if you take a quick look at my slide here, you'll notice that the percent of available chlorine goes down in general with age. Well, in this particular case, the y variable will be the percent of available chlorine. that depends on X, the number of weeks since it was produced. And we'll add one constraint here, and that is that the lower acceptable limit for chlorine we're going to assume is 0.4. And what we're interested in knowing typically in a stability study is at what age will the product no longer be acceptable? At what age can we expect too much of the product to have a chlorine level below 0.4? Okay, well, let's get over to Statgraphics and take a look at this data. The first thing I'm going to do is I'm going to open up that data file. Here you see Statgraphics running with an empty data sheet. If I go to File, Open, Open Data Source, all the sample data for today has already been placed in Statgraphics data files. So I'll tell it to open up a Statgraphics data file. And the data file here is a file called Nonlinear. Now that may give you an idea, a hint of what's going on already in this particular data. But here we go. We have a sample of, I believe it's about 44 measurements, 44 samples, ranging anywhere between 8 weeks since it was produced down to 42 weeks. Now, the first thing I typically like to do with any data set, any new data set, is plot it. And here I'm going to start with something simple. I'm going to go to Plot, Scatter Plots, XY Plot. Let's put chlorine on the y-axis, weeks on the x-axis, and press OK. What that's going to do is that's going to bring up just a simple scatter plot of the data. And you can see pretty easily that as the product ages, as the number of weeks increases, the amount of available chlorine goes down. Now, you might remember from a previous webinar that we have in Statgraphics a nice scatter plot smoother. If I push this button right here, it'll pull up a dialog box which will let me smooth the data. And my favorite smoother is a robust lowest smooth, lowest standing for locally weighted scatter plot smoothing. It's a quick, easy way to get a visual picture of what's going on. And, it certainly confirms the fact that as the chlorine ages, as the product ages, the chlorine goes down. And I think you can also see a definite nonlinearity in that particular data set. Okay, well that's just visual. There's no mathematical equation there yet. So it's time that we actually go and fit one of these regression models. Now, all of the regression procedures in Statgraphics can be found on the Relate menu. And they're divided up according to whether you have one factor, multiple factors, whether you're dealing with attribute data, and so forth. In this case, I've only got one factor, 1x, and I'm going to start with the simple regression procedure. Now, to run the simple regression procedure, it's going to pull up a dialog box. And the dialog box is going to ask me, okay, where's your y variable? What's your x variable? Well, my y variable obviously is chlorine. My x variable is weeks. So I'll just click them into place and press OK. It's then going to offer to fit any of, I believe it's 27 different types of models. Now, the default here is the linear model. And most of us do believe in starting simply, and the linear model is about as simple a model as you can get. However, there are a number of other curves that you can fit, types of curves, and you'll see that in this case we might want one of those, but I'm not quite sure which yet. There's also an option here, in addition to the least squares fit, which is the standard way of fitting a line, to do some alternative fit. For example, there's something called a mean minimum absolute deviation regression, in which rather than minimizing the sum of the squared residuals, which least squares does, actually minimizes the sum of the absolute value of the residuals. Turns out to be a little less sensitive to outliers if there happen to be outliers. We're not going to do that. We're just going to take the standard model just go ahead with least squares. Now, in terms of the output I want to look at, I'd like to look at the analysis summary, the lack of fit test. That's interesting because it will tell me the lack of fit test whether the linear model is good enough. If it's not, we can ask it to try alternative models. And also, it's interesting to look at the residuals. As far as the graphs are concerned, I'll just take the defaults. And when I push OK, it's now popped up for me a analysis window. This analysis window has all of those tables and graphs and so forth that I was talking about. Now, let's take a quick look at the fit. Let me double-click up here in the upper right. What you see here is you see that data now with the least squares regression line, the linear regression line, and you can see it written at the top. Chlorine is 0.485 minus 0.0027 times weeks. In addition to the line of best fit, which is a straight line through the middle, you also see confidence limits for the line. These are 95% confidence limits for the location of the line at a particular X. The outer bounds are prediction limits. They are 95% prediction limits. Now, the outer bounds are actually the most interesting. So let me right-click, go to Pane Options, turn off the confidence limits for the moment. Now, why the outer bounds are so interesting is they tell me where I would expect, with 95% confidence, another sample to fall. So if I was to take some additional sample, I would expect it with 95% probability to fall within these particular bounds. Now, in terms of setting a good shelf life, deciding when to take the product off the shelf, for example, remember I said the minimum requirement was 0.4 in terms of available chlorine. And basically, you would notice that up until 20-some weeks, most of the product, definitely most of it, will fall above 0.4. Now, actually, these are two-sided bounds. It might be better to right-click, go to Pane Options, and ask just for lower bounds. A lower 95% bound is a line above which I expect to see 95% of the product. In a typical stability study, what you'll do is you'll go to your minimum acceptable limit, like 0.4, read across till you hit the 95% lower bound. And at that point, if you go any farther, then you'll no longer have 95% of the product above that specification. Okay, now before we do that, though, there was some question about whether the linear model was appropriate. Let's put this particular picture away for a moment and go to, well, first off, the analysis summary. That's in the top right. Here we see a number of things. We see the estimated intercept and the slope. We see an analysis of variance table. Now, there's a very important statistic, incidentally, on this analysis of variance table. It's the p-value associated with the model. Since that p-value is below 0.05, then I could say that there is a statistically significant relationship between y and x at the 5% significance level. Okay, so in general, in regression, small p-values correspond to statistically significant models. So since that p is small, below 0.05, well, it's way, obviously, it's well below 0.05. It's even below 0.01. So very highly significant model. The major statistic for how well we're doing is something called R squared. You notice here in R squared of about 75%. That implies that we have modeled about 75% of the variability in chlorine. Okay, the higher R squared, basically, the better the fit. Okay, so it is a statistically significant model. It's gotten 75% of the variability. But it may not be the best. And if I put that away and now go to the second pane, you'll see what we call a lack of fit test. A lack of fit test has two p-values, one for the model and a second for lack of fit. Now, the second p-value tests the adequacy of the model we've picked. A p-value below 0.05, such as this one, indicates significant lack of fit. Now, lack of fit is not good, so the fact that we have significant lack of fit here means that this model is not as good as it could be. Okay? This is one case where we'd rather not have a significant p-value, but in fact it is. Okay, well, that basically says the linear model is not good enough. Now, if it's not good enough, let's go down here and ask what models might be better. And one of the things Statgraphics will do, if you ask it to, is to fit a bunch of different models to your data. In this case, it tried to fit all 27 models and sorted them from best fit to worst fit. And you can see the linear model down here with an R squared of about 74.8%. There are quite a number of models that can do better. In fact, there are a couple at the top, squared Y reciprocal X and just reciprocal X, which will give you something like 87, 88%. Now, squared Y reciprocal X would mean that Y squared was a linear function of 1 over X. Reciprocal X means that Y is a linear function of 1 over X. Okay. Reciprocal X model is actually a simpler model. That's the one I usually fit to this data. It does quite a good job. And to see how well it does, let's go back here. Let's right-click, go to Analysis Options, and now I can ask for reciprocal X instead of the linear model. And you can see, in fact, that the procedure definitely does give us a better fit. Okay, now for the final answer to our question, which is when should we take the product off the shelf, if I right-click and pick Locate, that'll bring up a set of crosshair cursors. And if I can drag these actually with my mouse and interactively see where the curve or where the lower prediction limit crosses 0.4. And it's actually just at about 20 weeks. Okay, at 20 weeks, that's as far as I can go and still have 95% of my product above the specification of 0.4. Now, that's a typical stability study. Gives you an idea of how we could use regression analysis, for example, to pick a reasonable shelf life. Okay. Well, let's go to another example here. Let me go back to my PowerPoint. And you can look at these, again, if you download these particular slides. Those alternative models that simple regression fits are what are called transformable nonlinear models. Okay? In a linear model, Y is a linear function of X. In a reciprocal X model, Y is a linear function of 1 over X. So basically, by transforming the X variable, I can still use a linear model. Well, there are certain models that are inherently non-linear, where you can't just transform a variable and use linear least squares. The particular data that we've been looking at actually comes from a very popular book by Draper and Smith called Applied Regression Analysis. What they've suggested actually for this particular data is fitting the model that I'm showing on the screen now. Fitting the model where I've got Y being equal to A plus 0.49 minus A e to the minus b times x minus 8. Now that's an inherently nonlinear model. The only way you can fit that is using some numerical search procedure to find the best A and B. Now there is a procedure in Statgraphics. Let's go back to Statgraphics again. Under relate multiple factors for doing nonlinear regression. Now it's under multiple factors because it works for multiple factors, but it also works for a single factor. And the way it works is this. I put in a dependent variable, and my dependent variable is chlorine. I then type in a functional form that I want to fit. And the functional form in this case is A plus, see if I remember what it is. It's A plus 0.49 minus A. So here I'll type parentheses 0.49 minus A times E, that's the exponential function, to the minus the quantity weeks minus 8. So what I've done is, and I better not use an O, I better use a 0 here, 0.49, there we go. I've typed in, using a Statgraphics expression, the model that I want to fit. A plus 0.49 minus A times e to the minus b times weeks minus 8. Now I better get it typed in right or it's not going to be able to fit it. Now when you type it in, what's going to happen is Statgraphics will look at that expression. Anything that it recognizes, it'll recognize, for example, weeks. It'll say, aha, that's an x variable. Anything it doesn't recognize, like an A or a B, it's going to say, aha, that's an unknown parameter. So if I type in my function, and I hope I have it in right, and press OK, you'll see another dialog box asking for initial estimates of A and B. Now, it's going to do a search procedure starting at whatever initial estimates you get. And if your model's fairly complicated, you need to give it some decent estimates or it's not going to get to the global optimum. This happens to be a very simple function. I don't really have to worry too much. I just give it relatively small values, and the defaults are 0.1, and it should be able to find its way. Okay. One more dialog box gives you all sorts of options to help you control what method is used to do the numerical search. Now, in almost every case, you can just press OK, take the defaults, but all these search procedures do on occasion need some help to find the optimal solution. So there are a couple other methods, Gauss-Newton's steepest descent. There are different maximum iterations and stopping criteria that you can change. You'll have to read about that if in fact, the defaults don't work for you. But most of the time, you can just go ahead, press OK. And I'm also going to take the default output, and it will go ahead and fit a model for you. And there is that particular model fit to the data. Okay. Now, that's a plot of the model anyway. If I go back over here to the analysis summary, I can also see the equation. And here's a nice little trick for you. Suppose I wanted to put that equation on the graph. If I highlight that equation and press Control-C, it'll put it on the Windows clipboard. And I can then go back to the graph, go up and push my Add Text button, do a Control-V to paste in the equation, press OK, and it's now put that equation on the graph for me. Okay, so if the programmer didn't think to put the equation on the graph by default, you can go grab it, copy it to the clipboard, paste it on the graph to see what the fitted equation is. Actually, that equation turns out to be that curve over the range of the data very close to that reciprocal x. I've actually put them on top of each other. They're almost identical, believe it or not, over the range of the data. They extrapolate differently, but over the range of the data, they're very similar. Okay, so that's the nonlinear regression procedure. If you have a functional form, any functional form, and it can involve more than one x, you can type it in and have Statgraphics search for the optimal parameters. Okay. Now, again, I've got a lot to cover here, so I can see already I'm getting a lot of questions. You're going to have to let me talk here for about an hour to go through these examples. Then I'll go back, take as many questions as I can. The third example I wanted to talk about is the calibration problem. The calibration problem is a little bit different than the normal regression problem. In the normal regression problem, you typically take your x and try to predict y. At the calibration problem, though, things are turned around. In a general calibration problem, you take and observe a y and then try to predict x. Well, I've put here a very typical calibration problem. What we've done in this particular data set, and it's called calibration, you can play with it later, is we've taken 4 what I'm going to call golden samples. These are standard samples for which the value that I want to measure is known. You know, it may have been measured very precisely someplace else using some very expensive product. Anyway, I've got 4 golden samples, and I'm going to take 3 measurements on each of the 4 samples. So, for example, the first sample has a known value of 1. You can see I've measured it 3 times. I've come up with 0.82, 0.95, 0.87. So for each of the 4 standard or golden samples here, I've taken 3 measurements. Okay, and what we're going to do is take that data, we're going to build a regression model. Then what we're going to do is we're going to take another sample, the 13th sample, where we don't know what the true characteristic is, the dimension or the weight, whatever we're trying to determine. We're going to measure it, but then use the fitted regression to predict what the true value is. Now this is, I think, probably best shown again by going back to the program. So let me close off this data set. I'm just going to say File New, put this one away for a moment, and call up a data file called calibration. Okay. Here it is. I've got my 12 samples, or 12 measurements, actually 3 measurements on each of 4 samples. To fit a regression model, I'm going to go to Relate, One-Factor, Calibration Models. Now, this is going to work, incidentally, just like the first procedure, just like the simple regression procedure. I'll put in a y, I'll put in an x. The y, in this case, is going to be the measurements that I've collected. The x is going to be the known value. Okay. When I press OK, it's going to offer to fit, again, any of those 27 different models. I happen to know for this particular data set, the linear model works pretty well, so I'll just keep that as a default. And then we'll offer for me the same sort of output I'd get in simple regression. Again, I'll just take the defaults. Okay. Well, here it is. What it's done is it's gone ahead, taken these 12 measurements, and fit a regression line to it. And the regression line, you can see the equation at the top. Measured is a function of known. Okay, so I've taken the 12 measurements on my 4 standard samples. I fit a linear regression to it. Now let's suppose I take a 13th sample. Don't know what the real value on this sample is. But I go out and I measure it, and let's say I get 5.85. Okay? And now I want to take that measurement and predict what the true value is. I want to take a y and now go over and predict an x. Well, in this particular procedure, you can do that by just right-clicking, going to Pane Options. And you can ask to predict x at a particular y. So I'm going to ask to predict x at 5.85. What it's going to do now, it's going to actually draw a line from 5.85 over to the regression model, over and down. And it actually predicts that the true value is 5.85573. There's a little bit of bias in this particular regression line, evidently, because it predicts that the true value is actually a little bit higher than what we've measured. In addition to a prediction of what the true value is, it gives me a 95% confidence interval for the true value. Now that's pretty interesting. That's actually this confidence interval, this lower and upper limit, where the horizontal line at 5.85 crosses the upper prediction limit and where it crosses the lower prediction limit. So this interval right in here, horizontal interval in this case, would give me a confidence interval for the true x, given that I measured 5.85. Okay? And that's what I mean by the reverse prediction problem. Usually we're predicting y from x, but in this case we're actually predicting x from y. Right, I have my mathematical model based on my golden samples. I go out and I take an additional item, measure it, and then use that calibration model to predict what the true x actually is. Okay. Again, there's detailed documentation on each of these procedures that comes with Statgraphics. I'm just trying to give you an idea of what's in the program, because I think some of you may not have found some of these interesting regression procedures. Another interesting procedure that's in the program is a comparison of regression lines. It's a special procedure for taking data which is divided into groups. For example, here is a data file called SOAP. It's data file from two different lines, line 1 and line 2. The y variable in this particular data was the amount of scrap produced during an hour or something like that. The x variable is the production line speed. Now I'm interested in two things here. I'm interested in, first off, the relationship between y and x. How does the amount of scrap produced vary with line speed? But secondly, I'm also interested in knowing whether it differs from line 1 to line 2. Okay, so the kicker here, the new thing, is that there is a categorical variable, levels. Okay. Let me put this file away, and this time open up a file called SOAP, I believe it is. Again, I'm going to give you all these data files that you can download and play with. There it is. We have a number of measurements taken. I think it's 15 from line 1, 15 from line 2. Now, to fit this particular data, I'll go to Relate, one factor, see if I can get it, comparison of regression lines. The dependent variable is scrap. The independent variable is speed. The level codes is line, and that's the new one now. All right, let's press OK. Now, by default, it's going to go ahead and fit two regression lines, one for line 1, one for line 2. And they'll be totally different lines. I could, if I wanted to, tell it to assume equal intercepts or assume equal slopes, but I'm not going to do that. I'll just let it fit two separate regression lines. Then it's going to suggest some output. The default will be fine. And here we go. And as usual, the plot is probably the most informative. It's taken the data here, line 1, line 2, and you see a fit for scrap as a function of speed. Now you see a number of things. You see as line speed goes up, so does scrap. You can also see a definite difference between line 1 and line 2? Well, I say definite. Let's say an apparent difference. It looks like the slopes perhaps are a little different. It definitely looks like the line for line 1, the fit is higher than for fit for number 2. Well, to test statistical significance, actually, one of the default panes that comes up down here is called a further analysis of variance. And what it will do is it will give you p-values to test, first off, if there's a significant relationship with speed. And the p-value says, yes, there's definitely a significant relationship. Secondly, is there a significant difference between the intercepts of the two lines? Since the p-value is small, the answer is yes, the intercepts are significantly different. And then thirdly, is there a significant difference between the slopes? Now, here the p-value is 0.18. It's above 0.05, which indicates that there is not a significant difference between the slopes. Now, at that point, I could come back here, back to the graph, right-click, go to Analysis Options, and tell it, assume equal slopes. And now it's gone ahead and refit, assuming equal slopes, but again, allowing the intercepts to be different. Now, those of you who are interested in how this is being done, if you go back to the analysis summary, okay, this is the summary that comes up at the beginning, and scroll down. The Stat Advisor will actually show you the model that's been fit. The model that's been fit says scrap equals a constant plus something times speed minus something times, in parentheses, line equals 2. Well, line equal 2 is what's called an indicator variable or a dummy variable. It's true or false. If it's true, it's turned on, it's 1. If it's false, it's turned off, it's 0. Well, for that, you actually end up with two separate regression lines, one for line 1, one for line 2, with the same slope but different intercepts. Okay. An interesting procedure, the ability to actually go in, fit regression lines to different groups of data and test whether or not there's a significant difference between the groups. Okay. All right. Well, that's the last example I have for a single X. I need to get on here and talk about what we do when we have multiple variables. Now, if you attended the first webinar, one of the data sets that I looked at was called countries. It had information about almost 200 different countries around the world. You know, what the population was, what the area was, what the population density was, and a particular variable that I found interesting in that particular data set was infant mortality. Infant mortality shows for each one of the countries how many deaths there are per live birth. And it varies an awful lot. You can see it varies from about 163. You can see in Afghanistan, in Andorra, it's only 4.05. So a lot of variability in infant mortality. I thought an interesting thing to do with this data is to see what other characteristics of the countries might be related to and capable of predicting infant mortality. So let's go back to Statgraphics. Let's put away what I was just doing and open up this particular data file. This particular data file is called countries. Okay. You can see it's got a lot of information. Here's the infant mortality column, deaths per 1,000 live births. Things that might be related to that could be the GDP, the gross domestic product, the percent literacy, how much arable land is. I don't really know. Well, I'm going to show you two ways that one can do some data mining. One can take a data set like this and try to come up with an interesting mathematical model for it. The first one will be under relate, multiple factors, multiple regression. The way multiple regression works is you start off and you put in a particular dependent variable, what you want to predict. And in this case, I'd like to predict infant mortality. You then put in a set of predictor variables, a set of x's, which you think might be related to infant mortality. Now, I'm going to pick 9. I'm going to pick population. That's the population of the country. I'm going to pick population density. That's people per square kilometer, I believe. Let's put in the amount of coastline, the net migration, whether people are leaving or coming into the country, GDP, literacy, phones, percent of arable land, and perhaps percent of the economy that's in the service sector. 9 different potential predictor variables of infant mortality. Okay. If I push OK, the next thing that will happen is a dialog box will come up asking me what sort of procedure I want to use. Now, if I leave it on the default ordinary least squares, it's going to fit all of the variables. Okay. However, I'm not really sure that all the variables are important, so I'm going to pick instead what's called a backward stepwise selection procedure. You know, backward stepwise selection, what it will do is it will start by fitting all of the variables. It'll then check the p-values on each of the variables, and if there are any that have a p-value less than what it says in the bottom right here, the p to remove, then it will remove those variables from the model. And it will one by one remove the least interesting variable until it gets down to a model with just significant predictors. Oh, and by the way, it also does a check as it removes variables of whether any of the variables that were removed early on might want to come back in, and sometimes they do. And there's a p to enter value here. And if anybody who was removed early on becomes not significant or becomes significant again, they can come back into the model. Okay. Well, let's just go ahead and press OK and see what it does. And again, I think all the defaults will be fine. I'll just press OK. And there it went. It went and fit a mathematical model to the data. And here it will summarize the variables that it picked. It actually picked 4 variables out of the 9. It picked net migration, GDP, literacy, and service as significant predictors of infant mortality. And you can see over here all the p-values are below 0.05, so the variables that it's left in the model are all statistically significant. You'll see down here the statistics. There's an R-squared, 69.4, and actually an adjusted R-squared. The adjusted R-squared is typically different if you've got, you might be comparing models with different numbers of variables. The R-squared statistic typically represents proportion of variability, or percent of variability in this case, explained by the model. That's penalized a little bit in the adjusted R-squared if you put too many variables in the model. It says adjusted for degrees of freedom, so you actually penalize complicated models compared to simpler models. Now, here is the mathematical model, by the way. If you look down a little bit lower, you can actually see the equation for infant mortality. It is a linear function of net migration, GDP, literacy, and service. Now, one problem here. If I go back to the graphs, okay, in particular, take a look at this graph. Here I have a graph where it's plotting the studentized residual versus the predicted infant mortality. In this case, it's taken that equation and predicted what the infant mortality should be according to that model for each of the countries. Looked at the difference between what was observed in that country and what was predicted. Okay? That's called the residual. It then studentized it, meaning that it re-represented it in terms of number of standard errors away from the model. So something like this value up here, which is near 5, says there's a country right there that was 5 standard deviations away from the model. Now, normally anything more than 3 standard deviations in a regression is a very suspect point. And you've got a couple here, one bigger than 3, one bigger than 5. Now, one other problem, though. If you look at this particular data, you'll see what looks like a funnel pattern in the data. Okay, that is a sign of what we call heteroscedasticity. Heteroscedasticity is a real fancy word for variability changing with the level or the mean value of y. In this particular model, if the predicted infant mortality is small, all the points are very close to the line. On the other hand, for countries with large predicted infant mortality, there's much more variability. All that means is it's not fitting the model very well. It's actually giving too much weight to some countries because they're highly variable, less weight to other countries. Now, there are 2 solutions typically to heteroscedasticity. One is to do what's called weighted least squares, okay, where you assign different weights to each row in your data file. But to do that, you have to know something about how variability changes with values of y. A simpler procedure that sometimes works is to take the logs of the data. To simply go back to the data input procedure, and instead of building a model for infant mortality, build a model for log of infant mortality. So I'm going to go back and change from infant mortality and just type in log of infant mortality and ask it to refit. And now it actually refit, and I'll show you the model in just a moment. But you can see actually that it did a quite good job of getting rid of that funnel type effect. Now the interesting thing actually, a couple interesting things. If I go back here, you'll see that the variables now entered into the model are different. It now wants 5 variables. It wants the population density, the GDP, the literacy, the phones, and service. Okay. It also got a considerably better R-squared. You can see an 81% or 80.5 on an adjusted level. Now, the reason it picked different variables may be that these X variables are related, are themselves related. So depending upon what metric you're working with, infant mortality or log infant mortality, it may pick up some variables in one case and different variables in another. But it's definitely a better model, and if you want to see the mathematical model, here it is down here. It's just a model now for log of infant mortality. It's amazing how good a variance stabilizing transformation actually the log can be. Now, one other thing I wanted to point out, another feature in Statgraphics, on any scatter plot, we have the ability to label points. I think I showed you this in an earlier webinar, but it's really useful here. If I go to this button, the Identify button on the Analysis toolbar, put in country as the variable I want to identify, and then say click point to label, I can now go click on points like this point right here, and see that Bermuda, for whatever reason, seems to have an unusually large positive residual. Infant mortality in Bermuda is larger than I would expect given the patterns in the other data points. The country with lower than expected infant mortality, most extreme, is down here. It's actually Cuba. So for some reason, those are both at about 3 standard deviations from the model. Now, one other feature, this is sort of nice. So when I looked at this at first, I said, okay, where's my country? Where's the United States? Well, if you haven't seen this before, if I go up to the analysis toolbar right now to where it says Cuba, type in my country, which is United States, and then push the binoculars right alongside, it will light in red the United States. You can see it's right about there. If I click on it, you'll see that that's the United States. It's a handy little feature in Statgraphics. Once you've defined an identified variable, you can go up to this labels field, push the binoculars, and it'll find that country for you. United States also does not do very well with respect to infant mortality, and that is one of our major health issues, actually. Okay, well, that's a stepwise regression. There's one other procedure that I wanted to show you that's also good for picking regression models. It's under Relate Multiple Factors. It's called Regression Model Selection. Now, what the regression model selection will do, by the way, is it will fit all possible regressions. Now, actually, before I do that, I want to go back and to where I specified my variables for multiple regression. I'm going to highlight them, press Control-C. All that did was take those names, put them on the Windows clipboard. Okay. Now let me go back to the menu. Now let's go to Regression, Relate Multiple Factors, Regression Model Selection. I'm going to go to where it says Independent Variables and press Control-V. That way I got from the Windows clipboard that same list of variables that I used in multiple regression. Okay? Where it says Dependent Variable, I'm going to type LOG open parens. Then I'm going to hold the Control key down, double-click infant mortality, and it'll put it right there, close parens. A couple little tricks to save me time in terms of putting in the different variables. If I now press OK, what the procedure is going to do is it's going to go and fit all possible regression models, by default involving anywhere between no variables and 5 variables. Well, heck, why don't we go to 9 variables? I'll now tell it to fit all models between no variables and 9 variables, and I'll press OK. And I particularly like in this particular procedure what's called the best adjusted R-squared table. Okay, so let's press OK. There it went. It fit 512 models, all combinations of the variables. And in this particular table, it's now listed them according to the adjusted R-squared statistic. Highest adjusted R-squared was 80.7. That actually involved 7 different variables. Well, that's rather complicated. You can get a 5-variable model with about an 80.5, you notice right here. A 4-variable model with about 80.2. A quick way of fitting all possible regressions, all possible combinations of the variables, and listing in decreasing order of adjusted R-squared, all of those models so you can pick different ones to look at. Okay. Well, that's an alternative to the stepwise regression. Actually, the stepwise regression, I noticed, actually got me to this model right here. So in this case, at least, stepwise regression actually did pretty well. Although if you wanted to ask what's the best 4-variable model, well, there's one, and so forth. Okay. Now, all the examples I've looked at so far involve a continuous response, a response variable that can be measured over some continuous range. Sometimes you come across data of different formats. Sometimes, for example, your data may be in the form of proportions, your response data. Or the response variable may be binary, zeros and ones. In that case, what you're going to want to do is something called a logistic regression. Now, I have two sample data sets here. One having to do with fabric, one having to do with the birth weight of babies. Take a look at the one on the left. This is data having to do with testing samples of fabric. The fabric in this case was subjected to 5 different loads. The loads being identified as 5, 35, 70, 80, and 90. A certain number of specimens were taken for each load. So for example, they took 600 specimens that were subjected to a load of 5. And then they counted the number of failures. There were 13 failures out of the 600 specimens. What we're interested in knowing is how does the percentage of failure change as a function of a load? Okay? Now, since percent failure has to be between 0 and 1, 0% to 100%, we wouldn't want to do just a standard regression because a standard regression might predict minus 5% failures or something like that. Hence, as you'll see in just a moment, a logistic regression. The second data set is an interesting data set. It comes from a book on logistic regression by Hosmer and Lemishow. We have the reference a little bit later on. What they did is they looked at a number of births in a hospital. Something close to, I think it was 200 births. The babies that were born were classified as either having low birth weight or not. If it's a 0 here, it was not a low birth weight baby. If it's a 1, it was a low birth weight baby. Every line in this file, every row in this file is a baby. We also know for each baby some characteristics of the mother. We know the age of the mother, the weight of the mother, whether or not the mother was a smoker, and how many times the mother visited the doctor in their first trimester. Again, the response variable here, well, it's only 0 and 1. So we definitely need some special ways to handle that particular data. Now, the way that this is traditionally handled is by defining a logistic model. Now, I have written for you here on the screen, and you can look at the PDF file that describes logistic regression for more detail. The basic logistic model starts and defines the probability of an event as the probability that something occurs at a particular combination of x's. For example, what's the probability that the fabric fails? Or what's the probability that we have a low birth weight baby? Okay. The probability of an event is expressed according to the equation shown here, equation 1, where the probability of the event is 1 over 1 plus e to a linear combination of the x's. Now, that is the logistic model. It has a very nice property that it ranges between 0 and 1. Never goes outside the range 0 and 1. Okay, a linear model, standard linear model, could easily go outside the range 0 to 1. Not that. Or if you re-express that, if you take the probability of the event and divide by 1 minus the probability of the event, which incidentally is typically defined as the odds of an event. Odds is probability of an event over 1 minus the probability. The log odds is an exponent, is e to the linear combination of the x's. Now, you obviously don't have to worry about all this. We'll let Statgraphics do the dirty work, but that is the general logistic model. Now, let me show you quickly how this works on those two data sets. The first data set I want to look at is the fabric data set, and I have it here under something called failures. Only 5 rows in this particular data set. You see the load of my 5 trials. You see the number of specimens and the number of failures. To do a logistic regression to fit this, I would go to relate attribute data and pick logistic regression. Now, there's 2 I could pick. I could pick either logistic regression or probit analysis. A probit model is an alternative to a logit model, but they both run the same, so I'm just going to do the logistic regression. Okay, now, the dependent variable in a logistic regression is supposed to be the probability of an event, or the proportion of failures. To run this particular procedure, I'm going to have to first put in failures and then divide it by specimens. If I take failures and divide by specimens, you'll see that'll give me the proportion of failures. This is another time when it's handy in Statgraphics to be able to just type in an algebraic expression. I also have to put in specimens for the sample size, and then I'll put in load as a quantitative factor. You'll see that the logistic regression actually will take either quantitative factors, that would be something continuous like load, or you could also put in categorical factors, line 1, line 2. It actually takes either one. This is a relatively simple one. I'll just press OK. Lots of various options. Usually you don't have to do anything again but press OK. OK. And here we are. Here is the fitted model. The fitted model for proportion of failures, or the probability that I'll get a failure as a function of the load. You see the model is somewhat curvilinear. In fact, it's constrained to be between 0 and 1. If I extended this out farther, it would asymptote at 1 as we went to even higher loads. You see a plot of the fitted model with confidence limits. Okay? Now, a couple things I look at when I do this. If I go back and look at the statistics, you'll see some new types of output. You'll see, for example, instead of an analysis of variance, you'll see an analysis of deviance. Well, analysis of deviance is similar to an analysis of variance. But since we're no longer working with data following a normal distribution, it's not really appropriate to talk about variance. So we'll call it analysis of deviance. Of particular interest is a statistic down here. Well, 2 things of interest. First, the p-value for the model. It's below 0.05. It's statistically significant. Second, the percent of deviance explained by the model, 88.6. That's like your R-squared statistic, which shows that we've explained about 89% of the variability in those failure proportions. Okay. Down here, you have an individual test of the statistical significance of each factor in the model. Well, there's only one factor. It's load. It's highly significant. The p-value is less than 0.05. Also of interest, the odds ratio. When you fit a logistic regression, there's a very nice interpretation of the coefficients. The coefficients show you the change in the odds. The odds, for example, that something will fail per unit change in X. This odds ratio right here of about 1.03 says that the odds of a failure increase by about 3% for every unit increase in load. So if you went, for example, from a load of 5 to 6 or 30 to 31, we would expect the odds of a failure to go up by about 3%. So one of the nice things about a logistic regression is that you can interpret the results. Now, this is even more interesting on my second data set. If I close this off and open my second data set has to do with the birth rate of babies. Okay? Here it is. It's a sample of about 200 babies. Some were low birth rate, some were high birth, not low birth rate, not low birth weight. I wonder how the odds of having a low birth weight baby vary with age, weight, whether the mother's a smoker or not, and how many doctor visits they had. Okay? Very nice data set to do a logistic regression. So let's go in here again. Let's go to Relate, Attribute Data, Logistic Regression. In this case, the dependent variable is binary, right? 0 and 1. Okay. I will not put anything where it says sample size. For binary data, you don't. I'll take all 4 of the variables, though, age, weight, smoker, and doctor visits, and put them in as quantitative factors. When I press OK, I'll get the Analysis Options dialog box. And as I did with multiple regression, I'm going to ask for a stepwise selection, a backward selection of the variables. I'll then press OK, OK again. And it's gone ahead now and fit the data for me. Well, particularly interesting in this particular data set is it picked out 2 factors as being statistically significant. It said the weight of the mother was statistically significant, and whether or not the mother was a smoker was statistically significant. Now, the effect of weight is negative. Actually, there's about a 1% decrease in likelihood of getting a low-weight birth baby for every additional pound of the mother. So at least in this particular data set, the heavier the mother, the less likely it was to get a low birth weight baby. Okay? An odds ratio of about 0.985, close to 1.5%. More striking, though, to me when I looked at the data was the odds ratio on smoker. If the mother was a smoker, it increased the odds of getting a low birth weight baby by almost 97%. You were almost twice as likely to have a low birth weight baby if you were a smoker. Okay. Very nice interpretation of the coefficients in a logistic regression. And remember, a logistic regression is used when the response variable, when the y variable is either a proportion or binary 0, 1. Okay. All right. Well, that's a logistic regression. One more regression to show you, and that is a Poisson regression. Poisson regression is used if the response variable is a count. Now, I pulled another data set here for you, a data set out of a book by Ray Myers on different types of regression. He looked at different mines in West Virginia, different coal mines actually, and wanted to build a model to predict how many injuries would occur in different mines. The columns in this particular file, the response column, the Y, is going to be injuries. The X variables, well, he picked 4 characteristics of the mine. The thickness of the inner burden, which, as I remember, was the distance from the floor of the mine to the lower seam, the lowest seam of coal. The percent of coal that was extracted from the previous seam, the height of the lower seam, and the number of years since the mine was open. What we want to do in this case is build a model for injuries. Injuries is the Y, the other factors are the X's. Now, what's different here? Well, Y is discrete. I'm not going to be interested in predictions that give me a minus 1.5 or something like that, right? So we have to do something special to handle the counts. Well, the way you build a Poisson regression model, well, you start by making an assumption. We first assume that at any particular combination of the X's, any particular X, if I took multiple observations, those observations would follow a Poisson distribution. And I've written a basic Poisson distribution, P of Y equals lambda to the Y, e to the minus lambda over Y factorial. Okay? If you've worked with a Poisson distribution before, that's what you're interested, or what you'd be familiar with. What's going to be interesting here, though, is unlike a lot of cases in the Poisson distribution, the rate parameter lambda is not going to be constant. It's going to vary from mine to mine. And the most common assumption is what's called a log linear link function. We will assume that the log of the rate parameter lambda is basically the number of injuries per year, for example, that the log of the rate is a linear function of the X's. Now, that's an assumption, but it's an assumption that tends to work fairly well in a lot of cases. All right. Well, let's go back to Statgraphics, and let's just pull up that final data set. I've got it in a data file called mining. Here it is. You see the number of injuries, and you see 1, 2, 3, 4 potential predictor variables. To do a Poisson regression, you go to Relate, Attribute Data, and now there are 2 that will handle counts. The Poisson regression and the negative binomial regression are both designed to handle counts. Poisson regression is the most common. Negative binomial is an alternative that could be used at some time. So let's go ahead and pick the Poisson regression. Now, it works very easily. You put in the number of injuries. You put in any quantitative or categorical factors. Okay. You press OK. And again, since I have multiple factors, I'm going to ask for a backward selection and take all the defaults. And it's now going ahead and fit a Poisson regression. Okay, this will be similar to the logistic regression. There is a p-value for the model. It's small, so the model is statistically significant. There are p-values for each of the factors that it's put into my model. And it's picked extraction. That was the percent extracted from the previous seam, and also the number of years that the mine's been in operation. Okay. There are, up at the top, things called rate ratios. and they show me the estimated change in the rate of failures in this case, per unit change in the variables. So for example, here I have the years that the mine's been in production. I have an estimate of minus 0.038 of the regression, but more important, a ratio of 0.96. What this says, this 0.96, is that every year that the mine is in operation, the rate goes down. Well, it becomes about 96% of the previous year. So if I go from a mine that was in production for 1 year to 2 years, I expect to see only 96% as many failures the second year. And then 96% of that the third year, and 96% of that the fourth year. The rate ratio is like that odds ratio, but in this case it tells me for every unit change in the X, what's going to happen to the rate. Well, you can see it'll go up by 6% for every unit of extraction, but it'll go down by about 4% for every year. Okay. You can also see these incidentally graphically, but you can only see them one variable at a time. Here's a graph of the fitted model, but I'm going to have to go to right mouse pane options. And for example, change, right now it was plotting it versus thickness, which was not in the model. It didn't like thickness, but let me pick a particular factor, extraction. Okay. And now you see at particular values of thickness, height, and years, the rate of injuries as a function of extraction. And what we're plotting here is basically number of injuries per year. And you can see it increases quite a bit from a low of 50 units, 50 feet on extraction up to 90 feet on extraction. Okay. Same basic principles, only difference here is we're working with data that are counts. All right. Well, again, I apologize for going a little long. There's so many interesting things to talk about when you talk about regression. Let me just give you as my last slide here the references from which I've pulled the data. There's a very good book, well-respected book on logistic regression by Hosmer and Lemonshow. A famous book on general regression by Draper and Smith. A good book on both regression and analysis of variance called Applied Linear Statistical Models by Kuttner and several other people. And then Ray Myers had that an interesting book that talks about things like Poisson regression. And as I told you, you can go ahead and download this. If you go to www.statgraphics.com, look for the link for the webinars. I'll be putting all of these data sets up for you. There's a PowerPoint presentation there, and hopefully if the recording worked out well of the webinar by this afternoon, we'll also put up the recording. Okay, well, I thank everybody who is still here. I did go a little long. I am going to try to answer a few questions, though. Oh, it looks like actually almost everyone is still here. I guess that's a good sign. Let's look at some of the questions. Okay, oh, I think we have a lot of questions. Well, yeah, about 13 questions. I'll stay as long as people are still listening. Okay, first question was, I missed which icon button you selected to do the scatter plot smoothing. Oh, you need to know this button. Let me call up that original data set that I'd used. It was the data set called Nonlinear. And And I had gone in to do an XY plot to put chlorine on one axis and X on another. Whenever you get a scatter plot, if you want to add a smoother to it, you first double-click on the graph to make it large. You then go to the analysis toolbar, that's the lower of the two toolbars, to an icon that has two arrows and some points with a smooth line. Now, this actually it has two uses. That's why it looks so strange. It smooths a 2D plot and rotates a 3D plot. We saved a little real estate by doubling up the function of that button. If you push the button, though, a smoothing option will come up, and I almost always choose robust lowest to put the smoother through it, and the slider bar will actually change the amount of smoothing that's done. The smoothing fraction is the size of a window that's passed along the x-axis when you smooth the data. And if you play with that, you'll typically get something that gives you a good idea of the underlying trend. Okay. Question 2. Robust lowest uses the least squares sum to fit the line. Okay. Robust lowest actually does what's called a weighted least squares fit. What you do is you take a window a certain width along the x-axis. You pass it through the data, left to right, along the x-axis. At any point along the x-axis, you fit a regression line to the points within the window. But not in just a standard regression. You do a weighted regression, giving more weight to points in the middle of the window, less weight to points toward the edge of the window. You also do two passes. You do a first pass where you smooth the data using this weighted least squares procedure. You then measure how far the points are away from the smooth. And you do a second pass, down weighting while you're doing the regression anybody who in the first pass was far away from the line. That's why it's called robust. It has the effect of down weighting any real outliers, so that a single point in particular far away from the line, far away from everybody else, won't affect the smooth as much as it would. It's a two-pass smoother, an ordinary weighted pass and then a robust pass where you downweight anybody who was far away from the smooth of the first pass. Third question, what is select in the X, Y select window? Every procedure in Statgraphics begins with what we call a data input dialog box. Every procedure has a select field in addition to the fields that are normally used to specify the data. Now, the select field is used to select a subset of the data. I can type, for example, first parentheses 10 in the select field, and it would just take the first 10 observations. Or, more interestingly, I could type weeks less than 30, any of various Boolean expressions. And then if I press OK, it would give you either, oops, almost left the webinar. No, I don't want to do that. Just want to get my window out of the way. Anyway, it would select for the analysis just observations meeting a particular condition. Okay, so going back to that data input dialog box, every procedure lets you do this sort of subset selection on the fly, which makes it a lot easier than going and having to mess with your data file if you wanted to restrict your analysis based on some conditions. Okay, let's see. Question number 4. What is the p-value and the F ratio? Well, whenever we fit a regression line and do a statistical test, let's say I go in and I do a simple regression, chlorine versus weeks. Let's just do this again. Okay. We test the statistical significance of the model, the regression model. And here you can see an analysis of variance table. By taking the variability in the data and splitting it into 2 pieces. Okay. In particular, we split the variability of the data into a piece attributable to the model and a piece attributable to the error, the epsilons that I started the talk with. Okay. In this column actually called mean square, it estimates what's called the variance due to the model and the variance due to the error term. We test the statistical significance of a regression model by taking the ratio of the mean squares, by taking the mean square of the model, dividing it by the mean square residual. The ratio of the mean square of the model to the mean square residual is the F ratio. Okay, 124.88. Now, that really has no meaning, nothing I can hang my hat on anyway, 124.55. It just says the mean square of the model is about 125 times the mean square of the residual. What's interesting is the value in red. It is the p-value. The p-value tells me, and this is the way I like to think about it, the chance I would have gotten my data if there was nothing going on. You know, what is the chance I would have seen this type of a pattern, or better yet, this type of a pattern if there was nothing going on? If p is small, if it's less than 0.05, it basically indicates that this is more than just chance. This is a real significant relationship. And we would say whenever the p-value for the model is less than 0.05, the model is statistically significant at the 5% significance level or the 95% confidence level, whichever way you want. You'll see, for example, that the Stat Advisor has done actually an interpretation down here. It says since the p-value in the ANOVA table is less than 0.05, there is a statistically significant relationship between chlorine and weeks at the 95% confidence level. So it basically tells you whether you've got a significant model. If that p-value for the model was above 0.05, it would basically say the model's not useful. It's not picking up anything significant. In this case, though, it's quite small, so it's picking up something quite significant. Okay. Oh, another question. I knew this was going to come up. What does the Durbin-Watson statistic tell me? Well, the Durbin-Watson statistic is a statistic that was invented basically for looking at time series data. You know, there's a general assumption when you do a regression, and that is that if you look at the data, the errors in the data, the epsilons, are independent from one row to the next. That whatever happened here had no effect on what happened here. If you're collecting data over time, that often is not true. There is often a significant autocorrelation in the data. If you look at January, February, March, April, well, March and April might be correlated. One of the assumptions of a regression, though, is that they're not correlated. And Durbin and Watson came up with a statistic to tell us whether there was autocorrelation in the data. Now, if the p-value on Durbin-Watson is small, it means there is significant autocorrelation. Okay, it means a problem, and for this linear model, that would indicate some significant correlation. Now, this is not time series data, but if you go back and look, for example, at these residuals, these are again the studentized residuals as a function of weeks. You can actually see what looks like a U-shaped pattern in this data. There is a correlation in this data as a function of X. Not because of time, though, but because the model that we fit is not the right model. Remember, let me turn off these confidence limits again. Remember, we have fit a linear model where we actually should have fit a curvilinear model, at least right here I did, which causes the initial residuals, the initial points, to all be above the line, the next points below the line, the next points above the line. That's causing this Durbin-Watson to be statistically significant at a 0.0001. But that's all it's really picking up in this case. It's mostly used for time series data. Okay. Can you plot the 95% lower limit on nonlinear regression as you did? No. I don't think so. The question is, on the nonlinear regression, you went in and you had an option to plot a 95% lower bound rather than 95% two-sided limits. Can you do that as well in the nonlinear regression procedure? I'm pretty sure the answer is no. I'm going to have to add that as an option. In fact, if you would, whoever asked that question about whether we can do this same lower bound in nonlinear regression, if you send me an email, I'll try to get that in the next release. No, I did it specifically in simple regression for people that were doing stability studies, because stability typically requires just a one-sided sort of analysis. But I think I need to, I'm pretty sure that has not been added, this option here to do either two-sided or one-sided bounds in the nonlinear regression, but I'll try to get it put in there. Yeah, anybody else, if you have good ideas after watching the webinar, just send it either to info@statgraphics.com or Neil, N-E-I-L, at statgraphics.com if you want to send it right to me. Seventh question was, how do you test for autocorrelation in regression models? I actually just answered that. You use the Durbin-Watson statistic. If the p-value is less than 0.05, there is significant correlation between adjacent observations, between the residuals from adjacent observations. One procedure to deal with that, incidentally, we have in multiple regression is called the Cochran-Orcutt procedure, where you can actually have it adjust for potential autocorrelation. I don't have time to talk about that today, but that would also be an interesting topic. Question 8, is there a way to do a simple linear regression with errors on both y and x? This is from, I believe, from Christian Charles, our dealer in France. I think, Christian, you know that I have not added that yet. He suggested that I add York regression or Deming regression, because often we do have, and it's a great suggestion, often we do have errors on both the y variable and the x variable. The standard assumption in fitting regression is that x is known without error, that I know exactly, for example, what the age of each of these samples is, that the only errors observed are on y. Well, there are cases where there may be errors on both X and Y, and there are ways of dealing with that. And we're going to be keeping a lot of people busy here, I can see, in the next a few months. Question 9, does forward and backward stepwise regression give different answers at the end? It can. You notice that in each of the multiple regression and logistic regression and so forth procedures, there are choices of doing backward selection or forward selection. In a backward selection, you put all the variables in the model, and then you start taking them out one at a time. That's what I usually do. There's also a forward regression, though, where you start with no variables, and you bring in the best one, then the next best, then the next best, and keep bringing them in as long as they're statistically significant. They don't necessarily come to the same answer. If you're worried about that, do it both ways. Do it forward, do it backward, and take whichever one gives you the highest adjusted R-squared. Because, no, they're not guaranteed to get you to the same place, particularly when the X's have what's called multicollinearity, when they're correlated with each other. Okay, question 10. What is DF in the example on infant mortality? Well, DF, wherever you see it in Statgraphics, does refer to degrees of freedom. Normally, if we're fitting a regression model, there'll be degrees of freedom for the model, which will be however many variables there are in the model. And there'll be degrees of freedom left for error. So in this case, I believe I went in and I did a logistic regression, right? This was low birth weight as a function of the different variables. I did a backward selection, and as part of the output, it gave me a table. Yes, DF here stands for degrees of freedom. There's a total corrected degrees of freedom, which is 188. That's actually n minus 1, number of observations minus 1. There are 2 degrees of freedom, 2 variables in the model. Remember, it picked, in this case, weight and smoker, and 186 degrees of freedom left to estimate the error. Degrees of freedom tell you how many pieces of information there are in the measures of variability or measures of deviance, and they affect the statistical tests, either the chi-square value or the F test. They're an essential part of looking up the p-value. Again, we're not typically worried too much about that. It's just the p-value, really, that I tend to concentrate on. Is there a comparison of alternative models in multiple regression like there is in simple regression? Not the same type. I showed you the one where it fit different combinations of the factors, but there is not, for example, a comparison of a reciprocal model with a log model or something like that in multiple regression. I guess that would be nice too, wouldn't it? Okay, we'll put that on a list of possible enhancements. Right. Is there a comparison of alternative transformations of Y in multiple regression? No, but that would be great. Okay, there's an audience question that was already asked. Where can you download this presentation? Go to statgraphics.com, look for the webinars link, and you'll see the downloads. Why were the data points used in the logistic regression analysis outside of the 95% confidence level? Is there a hint that we selected the wrong model? I suppose you're talking, which, I'm not sure where that would have been. Why were the data points used in logistic regression outside of the 95% confidence level. That must have been on the other example where I had gone in and I'd done the failures data, I believe, right? And I'd done a logistic regression. This is a good question, actually. Logistic regression where I took failures divided by specimens and fit a logistic regression as a function of load. I think what this was referring to was probably this particular plot. The question is, why are the points, a lot of the points, outside the confidence limits? Now, when we do regression, when we do different plots in Statgraphics, regression plots, you'll see two different types of limits. You'll see confidence limits sometimes. You'll see prediction limits sometimes. And sometimes you'll see both. If they are prediction limits, they are limits for the individual observations. If they are confidence limits, as these are, they are confidence limits for the mean response at a particular value of x. The way these confidence limits are supposed to be used is the following. You tell me, okay, Neil, what's the probability of a failure if the load is 40? Okay, and I might bring up my crosshair cursors and I might say, well, if the load is 40, I would predict, let me get this in here, that I'd see a proportion of failures, wherever that blue line is, about 0.146, 14.6% failures. Are you sure of that? No. That's my best guess. Well, what can you tell me with 95% confidence? Well, I can tell you with 95% confidence that it's somewhere between about 12.7% and 16.2, 16.3%. Confidence limits tell me how well I can estimate the long-term response, the average percent failures at something like a load of 40. Now, individual observations will very frequently be outside the confidence limits. That's to be expected. Okay, if these were prediction limits, then we would expect most of the points to be within the limits. But if it's a confidence limit, it's a confidence limit for the line, then often the points will be outside. All the points could be outside the limits for all I care, because it's a statement on the mean y at a particular x. Okay. Why didn't I choose smoker as a categorical variable instead of a quantitative variable in logistic regression? I could have done it either way. Smoker was 0 or 1. When I fit it, it was 0 if the mother did not smoke. It was a 1 if the mother smoked. Why didn't I choose it as categorical? I could have. You will remember when you do a logistic regression, you can specify variables as being quantitative if they're measured over a continuous range, or categorical if they're discrete. If something is only at 2 levels, it can be done either way. That's why, for example, in a designed experiment, in a 2-level factorial, for example, you can have both quantitative and categorical factors. I put it in as quantitative because it's easier to plot if it's quantitative. You get more options in terms of plotting things. But if a variable like smoker is just at 2 levels, it could have been put in either as quantitative or categorical. It would have gotten the exact same analysis, exact same statistical model, but I actually got better options for plotting if I put it in as quantitative. Okay, someone would like me to do an ANOVA and a MANOVA at the next webinar. Well, I can't do it for the next webinar because I've already scheduled the topics for the next couple, but I think the next one I haven't scheduled will be on analysis of variance. Okay, someone put in a comment, I perform a logistic regression with more than 32 variables. What can I do to find the most important variables? I gather that we have a limit of 32 X variables in logistic regression. I'll have to have someone check that. There's not a lot you can do at the moment, only we probably should increase that limit from 32 up to, I think in multiple regression it's 128 or something like that. So all I can tell you is I'll put in a note in logistic regression to make sure that the number of variables is as large as it is in multiple regression. You showed an example where you compare two regression lines. Can you compare more than two? Sure. Let me actually open up a file that I use a lot. It has data on automobiles, different makes and models of automobiles. I did an example where I did a comparison of regression lines, I think two. Let me do more than two. Let me take miles per gallon in highway driving. I hope you've seen this data file before. I use it in a lot of examples. Let me take the miles per gallon in highway driving versus the weight of my automobiles and plot it or fit it as a function of, let's say, let's try type of vehicle. Let's see how this works. Okay, here's an interesting one. Here I have fit a whole bunch of regression lines, one for compact cars, one for large cars, one for mid-sized cars, one for small cars, one for sporty cars, one for vans. Okay, so there are 6 regression lines. Highway miles per gallon versus weight for 93 actually automobiles by type of vehicle. Again, I had recommended that you look at this further ANOVA for variables in the order fitted to see if there was a significant difference between the intercepts and between the slopes. This is exactly the values you would have gotten if you did in ANOVA, an analysis of covariance. Framed differently, this basically is fitting miles per gallon versus highway, miles per gallon highway driving versus by type of vehicle using weight as a covariate. Okay. Since this was mostly a webinar on regression, I did it using our comparison of regression lines procedure. You could have done the exact same analysis using an analysis of covariance. You would have gotten these exact same statistics. Okay, but I find these plots really useful. Outliers. When do you take out outliers? What sequence do you follow? This is in relation to the 95% rule. In other words, do you fit the linear regression, then take out the outliers? Do you go to comparison of models first? What have you found to be the best? Well, that's an interesting question, isn't it? That's one of those chicken and the egg problems. For example, let me just call up that nonlinear file. By the way, I'm going to keep talking as long as there are questions. I enjoy doing this. So as long as people are listening, and I'm just going to keep talking. This is an interesting question, though. It has to do with outliers. Remember this data, chlorine versus weeks. Remember I started by doing a linear regression of chlorine versus weeks and got this particular fit. Okay, now, if you look at this particular fit, and let's just plot the prediction limits, not the confidence limits, you'll notice that all the points are inside the 95% prediction limits, right? I could also have gone and asked for unusual residuals. There's a table here, and that will identify any unusual residuals, and it actually doesn't find any. Okay? An initial look at this data, I'd say I don't see any residuals. Let's go and fit a different model. So then I went to analysis options, and I fit the reciprocal X model. And now, actually, there do appear to be a couple points outside the 95% prediction limits. This point here, row 17, this point here, row 18. And if you go back to the table of unusual residuals, the first one is a good 3.66 standard deviations away from the line. Now, one thing I didn't show you, but I can actually interactively take these out. I can click a data point, then hit the plus minus button. That's the exclude button on the analysis toolbar, and refit without that point. Okay, well, let's see. Then there's somebody about 2.94 standard deviations out. Maybe I'll take this guy out too. Well, now there's a guy 2.75. Well, the question was, obviously I don't want to keep taking out points. Question was, what appears to be best? Well, certainly on this data set, it seems to be best to pick the appropriate model, then take out the outliers, because they wouldn't look like outliers necessarily if you didn't have the right model. You then, though, might want to go back if you really thought these were outliers, and that's a whole nother question. Okay, you know, really we don't like to take out outliers unless there's an assignable cause. I mean, they're very suspicious, but, you know, I don't really like to take points out unless I can find a reason for it. But let's suppose I took them out. I might then go back and do a comparison of alternative models and see what the best model are. Well, they're still the same one, reciprocal X and squared Y reciprocal X, at which point I'm pretty happy. I think, though, and it is a little bit of a chicken and an egg problem, I think you typically have to go fit the model first, then look for residuals with respect to the model you fit, then potentially take out the residuals, but then go back and recheck and make sure that that's still the best model. Question 18. This is good. I love it when there's lots of questions. Can we display predicted values, Y for new X or calculated Y for X, with missing Y in the plot of the fitted model? I think what someone is asking is, can I go ahead and plot a prediction? Well, no. It must not apply here. Actually, the line of best fit, the regression line going through here, is the line of predicted values. For any particular X in a simple regression, the line here would predict the Y at that particular value of X. I suppose this must apply to multiple regression. Let me go and take again the example I had for multiple regression. Multiple regression, that was the one, I'm trying to remember what the data set was. That was the one where I had done, the birth rate data. Let me open up the birth rate data again. And remember, here I had actually gone and fit a regression model, I believe, right? Oh, no, that was my logistic regression. Oh, it was the countries data. I'm sorry. It was the data having to do with the different countries where I was trying to predict infant mortality. I had done a multiple regression, I believe. It was infant mortality versus population, a few of these variables, a few of these variables, and this variable, I believe. Right? Okay. I had asked it to do a backward stepwise selection, and it had gone ahead and done a fit. It had picked out, in this case, net migration, GDP, literacy, and service. Now, some of the plots that are available in multiple regression, one is, for example, the plot of observed values versus predicted values. Here, there is a plot for each point in my data file. Now, one feature I did not show you, but I could have, is we do have a reports feature. If I go to the tables and graphs button in most of the regression procedures, I can ask it to generate a reports table. Now, the reports table can display different things, including fitted values or predictions for data points not in the data file. Now, the way you do that, it's sort of interesting. You go back to the data book. Here's the data I had on countries. Let me scroll to the end of this data, past Zimbabwe, I think is the last one. Suppose I had some other country not in my data file, and I wanted to make a prediction. I had, for example, some new country. If I put in statistics for my new country, okay, let's say I put in an additional row in my data file. Let's suppose there were 10 million people, a population density of 50 people per square mile, no coastland, no net migration. I'm going to leave infant mortality blank. That's the one I want to predict. A GDP of, let's say, $15,000 per individual, a literacy rate of 90%, 300 phones per 1,000 people. 300, yeah, it's probably closer to 3,000. 300, let's say 10% arable land, and maybe 50% of the economy, 0.5 for service. In many of my regression procedures, you can go to the bottom of the data file, put in information on an additional data point, put in values for all the X's, but leave the Y blank. When you then go back to the table, the reports pane, it will make a prediction at that combination of the X's. So for my new country, with all those values I put in, it predicts an infant mortality of 29.44. Okay? I must have put in a strange country here. The lower confidence limits, or the confidence limits of for the forecasts, -11 up to 69.9. Well, that's one of the things that can happen, I suppose, in a general regression. You can get negative forecasts, even though I don't know how we get infant mortality of -11. Oh, but again, this was for infant mortality. I forgot to take the log transformation. I would have been better off had I taken the log transformation. I wouldn't have gotten perhaps such crazy forecasts. What I wanted to show you, though, is that you can put additional rows at the bottom of your data file and get a table with the forecasted values. Now, the question asked whether we can plot those additional points. No, you can't, but you can at least have the procedure make the predictions for you. Number 19, question 19. Are there any rules as to using regressions when you go to a time series analysis rather than these regressions? There are special things we should do if we're doing time series fitting. I'm going to have to reserve that for another webinar. I'm not going to answer that one in 5 minutes. Yes, there are special things to do when a regression involves data recorded over time. And I'll try to schedule a webinar to answer that question. Unfortunately, it's a good question. It's just a lot more than I have time to talk about. Question 20. Why do you extrapolate time in the chlorine stability data for the prediction limits and not the confidence limits? I didn't know we did that. I think what they're saying is that if I take data like my non-lin file, fit a regression model to it, let's say chlorine versus weeks, just redoing this linear regression here, and let's go straight to the reciprocal X model. We know that's a good one. The procedure does let you extrapolate. Oh, I see. I think what they're referring to is the fact that notice how these confidence limits go all the way to 50, but this one cuts off. That's just a scaling problem on the y-axis. If I go right mouse, graphics options, go to the y-axis, and change the lower limit to maybe 0.3 and apply that, well, that was maybe a little more than needed to be done. It was just that confidence limit being cut off by the scale on the y-axis. If you widen out the scale, actually it extrapolates both confidence limits and prediction limits. One warning, though, on extrapolation. You extrapolate at your peril. I mean, when we fit these models, the least squares fit doesn't care at all for what the model does outside the range of the data. Regression models are good in general for interpolation over the region in which we have data. We don't really know, unless we look, what might happen if we go outside the range of the data. The mathematical model will extrapolate fine, but what happens in reality, I don't know. And that brings up another point. When we fit these regression models, you really need to consider these as approximations to reality, not necessarily the theoretical model explaining what's going on, but an empirical model that models the data well over the region in which you've got data. Whether or not they will extrapolate is a whole other question. Okay. Someone is asking how I obtain the p-value from the F ratio. It's either using a chi-squared. Well, no, if it's an F distribution, it's from the cumulative F distribution. I can answer that for a specific value privately, but in general, when you see an F ratio and a p-value, the p has been determined by estimating the tail of the F distribution out past the displayed value of F. There was a question on the model fitting here of when I initially went in and fit a linear model to chlorine versus weeks, of why the lag 1 autocorrelation was 0.45. I'm going to have to talk about autocorrelation, I can see, in some detail when I start talking about time series. Autocorrelation is a measure of how correlated adjacent residuals are when you do a regression. You can see that there is some autocorrelation in these residuals. It's 0.45 with the linear model, but if I switch over to reciprocal X, you can see it all but disappears. Let me reserve that question until I do a webinar on time series analysis, and then we'll talk about the autocorrelation. Okay. Someone is requesting that we put together a Statgraphics theory guide, a separate manual. I can do that. I have tried actually in all the PDF files to use those data sets that come from different textbooks, where the textbooks do probably a better job than I can of explaining all the theory. But we'll try to do that. In fact, if there's anyone out there who would like to do a statistical theory guide to Statgraphics, we'd be very interested in hearing from you. There's only a limited amount of time that we have. So if there's someone at a university out there, let me invite you to contact us. If you'd like to collaborate, for example, on writing a Statgraphics theory guide, where we go into all the theory behind all the numbers, I would be happy to do that. Question 24, in general, how do you check for validity or reliability of your data set? Oh, that's a hard question, isn't it? How do you check for validity or reliability of your data set? Well, in some procedures, in particular, for example, in the general linear models procedure, which I did not talk about, you have the ability to exclude a certain subset of the data from the fit and then use it as a separate validation data set. For example, I think if I went in here and put in a general linear models procedure, chlorine as a function of weeks, and asked it to take a random 30 observations. Random is something that you can put in also in the select field. And press OK. It will fit a linear model to the data. And I believe give me statistics, yes, both for the estimation period, that is for the 30 observations that were used to fit the model, and the 14 that were randomly withheld. One good way to do validation on a model is to exclude a certain amount of data from the fit and then look at the statistics for the fit versus the statistics for the excluded data points. And you can see, for example, if you looked at the mean squared error, the mean absolute error, that they're very similar in the validation period from the estimation period, leading me to believe that the model is being fairly well estimated. I'm beginning to think I'm going to need a second webinar here on regression to answer all of these questions. Another question, question 25. How do we see multicollinearity in regression? What should you do if there's multicollinearity? Well, I'm going to have to, best answer to that has to do with looking at correlations and variance inflation factors. And what should you do if there's multicollinearity? Well, we also have a ridge regression procedure. I'm going to have to put that one off too. That one's probably going to take me a half an hour to talk about, and I'm really getting to the point that I'm going to lose the audience. Whoever put in that question on multicollinearity, it's a great question. I will answer it, but I can't answer it today. It's just going to take too long. 26, is it possible to use a comparison of regression lines with multiple regression? You can do it with indicator variables, but you can't do it, there isn't a special procedure for it. Another good topic for the next webinar. 27, someone argues that the 2 points I removed from the regression that for chlorine, remember I clicked out those 2 data points, could be removed because the measurement equipment must have been off that day or that week. Both bad points were measured on the same day. You know, I tend to agree that that they are likely to be bad data points. Remember, this was that chlorine data again, where I'd gone ahead and I'd fit a model to it. I'd gone ahead and done a simple regression, chlorine versus weeks. I'd fit a reciprocal X model. I did chlorine versus chlorine. Yeah, that's a pretty good fit. Chlorine versus weeks, that won't be quite as good. Remember these 2 data points, this one and this one? Very, very tempting to remove them because they appear to have been taken at the same time probably, and the equipment probably was off. If you read the discussion in the book by Draper and Smith, this is real data. They actually went back to the researchers who collected that data point and tried to find a reason, an assignable cause, and couldn't find one. Had they found an assignable cause, you know, bad equipment or whatever, they would have taken them out of the data set. They said they actually retained them in the data set because they could not find an assignable cause, and the conservative thing to do was to keep them. So yeah, I would have tried real hard to find out a reason probably to remove them. You know, they don't have a big impact on the fit. You can actually see the model doesn't change much. The bounds do tighten a little bit, so it could have an impact. In fact, I think it does increase the shelf life from about 20 weeks to 21 weeks, which could mean a lot of money, I suppose, where the line intersects. They don't have a huge impact, but they do have some. Someone else would like more information about parameter lag. Okay, well, I can do that, but only if I talk a lot about time series. And I'm well past the time that I've had allotted to talk here. So I'll tell you what we're going to do. We're going to take all of these questions. We'll take the multicollinearity question, the autocorrelation question, the parameter lag question, put them all together, and I'll try to do another webinar here in the near future to answer those. I just can't answer them in any reasonable way in 5 minutes. Okay, well, I can see that at least half of the audience was still with me, which is pretty amazing. So I do thank you for your time and attention.